As James said, my name is TJ Sego. We'll be working together for all 4 modules of the day for today, and all on a crash course introduction to Python programming. Now, a lot of what we will learn today will be specifically geared towards working on CompuCell in Python. So today's modules will be by no means exhaustive. The goal is not to make experts in Python out of all of you, but rather to get you to a starting point where when we start on the workshop beginning tomorrow, there are no deers in the headlights, so to speak, but that you can follow along, build models along with all of us as we're going through the various modules for CompuCell, and then hopefully in the hackathon to actually go off and work with your peers to work on your own projects while we roam around and support. So Python is a great programming language for a lot of reasons. In scientific computing and in computational modeling, Python is widely used for a number of applications in biological modeling. For those of you who took Herbert's course, by now you're probably quite aware that Python is used very extensively for doing network modeling. Python's very good for being able to take, say, implementations of existing models and adding new models to them. So modifying things that, say, others have developed that you would like to contribute to and adapt and improve or work from. Python's also great for doing analysis of experiments. So it's very straightforward to get into doing analysis of large data sets, doing visualization, statistical analysis, so on and so forth. Now, today we'll focus on just the very basics, and admittedly, there are basics about Python that we will not cover today. So today is almost exclusively reserved for supporting the CompuCell workshop. I would like to note that for those of you who may be interested in learning more, that we would be happy to provide additional learning resources. So there's a lot that can be done with Python in a lot of different applications. And if you're like me and have an interest in using software to do computational modeling in science, and would like to know more about where to find some of those resources and so on and so forth, you can send an email to one of us or enter into the chat or into the Slack channel, and we can connect outside of today's class. Just as a quick reminder for those of you who may have missed the pre-module informational session, today is being live streamed and recorded. So you are live on YouTube currently, and we'll also be recording this for reference as a learning resource for people going forward into the future. So just want you all to be aware of that. Now, I wanted to kind of start today with a couple of overarching points to sort of set the tone for today and make sure that everyone has a good sense of what to expect of what they learned today, what to expect from themselves with learning how to do programming using Python, and also from a logistical standpoint, what happens in the case of, say, loss of internet connection, practically speaking. So there's always the chance that I may get disconnected intermittently. I have in the past had intermittent internet connection issues. If that happens, just hold tight. Giuliano may pick up. Otherwise, just hold tight and I'll be back with you very shortly. Now, concerning our actual learning experience today, it's important to know that no one who works in software development knows everything about the software, programming language that they use. And so one thing to always expect when going into using programming to develop software is to always expect that you're going to have to learn something. Never expect of yourself that you should know everything about the language that you write in. There's always an element of learning something new. Something is always being developed, especially in a popular programming language like Python. Something new is developed every day. So there are always new tools. There are always improvements to existing tools. So you should always expect that you will be far from knowing everything. And that working on any project most likely will be, at least in some sense, a learning experience. And that may be even the case today. We may see this today where someone may have a question that I just don't know the answer to, and that's perfectly fine. We have lots of resources. The internet is our best friend in that regard. And so always expect this to be a learning experience. The internet is the best place for finding information to accomplish the things that you want to do. If you don't know how to do something, there are plenty of resources. Every decent package comes with at least decent documentation, CompuCell included. And so if you don't know how to use something, documentation online that's developed by the developers, are always a great resource to figure out how to do something with something that's been developed and made available. Other coders in the world are quite generous with their experience. You'll find that if you go to, say, stackoverflow.com, you can find lots of answers that have been submitted by other software developers answering specific issues. So something like, something like a Reddit channel where you can post questions and other developers can answer your questions. It's an invaluable resource for software developers, is to have that community of advice and experience that's given by their peers. Now, almost always when developing, some sort of solution in software in general, this is true in Python, in C++, in Java, and just about everything. There's almost never a unique solution to what you may want to accomplish. So because of the level of abstraction and the degree of functionality that comes with a lot of languages like Python, just about any time that you set out to do something, you'll find that you can generate lots and lots of different ways to do it. And so it's important to always keep in mind when developing software solutions, even for just very basic code, is to always focus on what you want to do. How you do something is never going to be unique, almost never going to be unique. And so what's important is to focus on what you want to do and experiment with different ways of doing it. You'll find that two coders trying to accomplish the same thing will go about it in two, say, similar ways, all the way to extremely different ways. So what's very important is to keep in mind the actual, functionality that you're trying to accomplish, the tasks that you're trying to accomplish with your software, with the code that you're writing. And probably most importantly is that, in my opinion, the number one key to success in software development is perseverance. Software can be maddening. For some of us, developing software is an emotional experience at times. And what's most important is, that you keep strong, you keep calm, break things down, say, working on a complicated task, break things down into, say, simpler tasks, and use the information that's available to you online, use the documentation that you have at your disposal, all the way to very basic textbooks, or YouTube videos like the one that we're making right now, and just hang in there, try things out, and you'll get there. So with that, let's start doing stuff. For those of you who don't have any sort of Python environment set up on your local computer, we're going to refer to the Tellurium app as discussed in the pre-day informational session. So We're going to migrate over to nanoHUB. I'm going to split my screen here, and we're going to do a little bit of work together. So let's start by migrating over to nanoHUB. If you're not there already, we're going to go to the nanoHUB Tellurium app. I will put the link in the chat. There's the chat, the link in the chat for everyone. That will take you to the web page that you see on the left-hand side of my screen. So this is the Tellurium app. The Tellurium app is a Jupyter notebook that has Python and Tellurium. We, by and large, are not going to work with Tellurium per se, but more so work in the environment that's been set up for Tellurium. So everyone would like to start by following that link. If you've not set up a nanoHUB account by now, then you should be prompted to create a nanoHUB account that looks something like what's in this screenshot here on the right-hand side of my screen. You may have to click the Launch Tool button on the Tellurium tool page to get here. But for those of you who try to launch the Tellurium tool and haven't created an account, you should find something like this. You can also just select the Sign Up button on the main nanoHUB landing page, which is just nanohub.org. And you can follow with whatever sign-in credentials you like to generate. Fill out a username and a unique password. Give everyone maybe just another minute or so in case not everyone has done this yet.
You want to use the poll to check if people are all into Tellurium?
Yes, let's do that. Looks like we've got a few people who still need a little bit more time. And of course, if anyone runs into any technical issues, please let us know. We can put you in a breakout room with either Jim or Giuliano to help get you back on track and along with the rest of us. Someone asks, can I just do this on Jupyter Notebook on my local host? Absolutely. So we'll start with a very quick example that does use Tellurium, but that is just for those who are not familiar with using Jupyter Notebooks. So if you have a setup locally and want to use that, by all means.
Or again, if you took Herbert's course and you have a collab version of Tellurium, that would be fine too. Is anyone else having trouble with the nanoHUB launch?
Remember that people can't unpost to the survey.
right, looks like we're going to do this again. Let's check in with everyone, see, make sure everyone. Yeah, there we go. Make sure everyone is with us so far. All right, looks like we're good. So let's continue. Appreciate everyone's patience. We've got quite a few of us. We want to make sure that we don't lose anyone along the way. So thank you very much for hanging in there. So for those of you who are using Jupyter Notebooks in some form or another, if you've not used Jupyter Notebooks before, we're just going to crash through how to use this for executing Python code very quickly. So in Jupyter Notebooks, every one of these little boxes is called a cell, and each cell consists of an executable section of code. So you can write whatever you'd like. And in these cells, you put some Python code, and then when you would like to execute it, you just press Shift Enter. So when your cursor is in an active cell and then you'd like to execute it, just press Shift Enter and you'll get a result. Now there's all sorts of other things you can do with this. You can say click on a cell and click on edit and delete cells. And in the case of the Tellurium app, that'll reset everything all the way back to just this first statement, which is to bring the Tellurium app into the executable code. So we execute things that we put in our cells by pressing Shift Enter on our keyboard. Now for the case of the Tellurium app, if you're using nanoHUB and the Tellurium app, the notebook that launches, so that opens when you launch this tool, is by default read only. This cannot be saved. And so in general, if you would like to store your work using the Tellurium app, whether today with keeping our exercises on your local machine for reference, or when working on something else, what needs to be done is to take this default starting notebook that's read-only and then make a copy of it. And in nanoHUB, you can make a copy in a drive that's yours. And that copy, you can save, edit, download, so on and so forth. And so you can do this by, in the nanoHUB tool, clicking on the menu bar, clicking File, and then select Make a Copy. And now you should notice in the top, in my original launch, the very top next to Jupyter, it just says Tellurium with this note that says read only. Now when I selected Make a Copy, a new tab was opened, and now I see this file is called Tellurium-copy1 with no note about being read only. So this is now a notebook that I can save. Now you can do saving procedures, downloading, and so on and so forth in the file menu as well. We're going to start by actually doing a very quick little example. So I'm going to put another link in the chat. This, again, is only for those who are using the Tellurium app. So you can follow this link to the documentation for Tellurium. We're just going to grab a little bit of code off of the Tellurium site. We're going to put it in one of our cells, and we're going to execute it. Oh, sorry, was there a question? Okay, no problem. Yeah, so link in the chat. This is to read the docs for Tellurium. So this is the online documentation. I have this pulled up as well. Now on the left, if you click the link for Quick Start, this will take you to the Quick Start page. And what we're going to do is we're going to select these 3 lines of code in this first sample called Simple Example. I'm just going to select all 3 lines of code and copy it and see if we can paste that into our Jupyter Notebook like so. For those of you who didn't take the Tellurium course, this is just specifying a very simple ODE model, simulating it for a number of simulation steps, and then plotting it. And that's all we're going to do. So again, the link to this page is in the chat. We're going to copy the 3 lines of code under Quick Start and Simple Example. We're going to paste those into our Jupyter Notebook and then execute it by pressing Shift-Enter. Now I get an error. I get an error. Let's see if we can fix it like this. Now you notice that I missed the first line of the code and ended up getting an error. It happens, and it happens all the time. We're going to see errors all day and all week. Totally fine. Said that it was missing something called TE, and that was because I forgot to copy the first line, and this did not carry over from the first cell. So when I fix that, then I have what's provided in the Quick Start manual page from Tellurium. So with all 4 lines, we should have something like this. Doreen points out in the chat that it could have just rerun the first cell. That is correct. So in Jupyter Notebooks, the execution of cells occurs sequentially from top to bottom based on what's been previously executed. And in this case, I have not re-executed my first cell. We're going to try to keep our work today as basic as possible concerning actually utilizing multiple cells. Jupyter Notebooks provides a ton of additional functionality for lots of interesting things. And so what we're going to try to do is keep all of our code that we execute for today's exercises all into individual cells. Yes, question, does run all work for doing multiple cells? Yes, it does. So Shift Enter will execute a cell, and then, yeah, under cell in the menu bar, if you click run all, then that will go from the top and go through and execute every cell from top to bottom. All right, so let's try this poll again real quick. Make sure everyone's with us. It's not critical that we have a strong understanding of the particularities concerning Tellurium right now. Probably what's most important is that everyone can get something into a cell, preferably the example provided in the Tellurium documentation, and can execute the cell and generate a plot. So James, can we restart this poll and make sure we haven't lost anyone along the way before we continue? Thank you. Polly asks if it's possible to save notebooks locally. The answer is yes. So you can save this to your drive on nanoHUB, and then you can also, in the file menu item, you can go to download as, and you see you actually have quite a few options. So you can download this locally as a notebook. You can also convert this to raw Python code. On nanoHUB, can save this as save and checkpoint. So again, that's in the menu bar as well. Under the file menu item, click save and checkpoint.
Somebody's asking for help. Could you raise your hand and if you need help?
Looks like there's also some questions about the model specification here. So this is Antimony model specification. And what this says is that as a species S1 converts to a species S2, and that occurs with a rate proportional to K1 times S1. And for initial conditions that aren't specified explicitly, as in for S1 here being declared as starting at 10, no declaration is made for initial conditions, and the value is assumed to be 0. So not critical for getting through today, but we will spend, I think, half of a day working in this world. All right, so it looks like we have someone who needs some help. Have we connected them with someone yet? Or we have break rooms set up?
So if, okay, I'll put them in a breakout room.
All right. So I'd say let's continue then. If you've not gotten to this point entirely, that's okay. We'll have lots of practice getting code executing, and lots more practice at dealing with errors, both today and through the rest of your career as Python developers. So let's start with a first very basic example, and I'm just gonna do this interactively along with you. You can, again, reset your notebook by going in the menu bar to edit and delete cells. For the Tellurium app, that should just reset it to having the import statement at the beginning. And we're going to do a very basic exercise of doing an actual calculation. It's not super important that you understand how exactly all of this is working, but we're just going to do a basic calculation of adding two integers, and we're going to do this like follows. So let's say that we have two integers, and we're going to call them a and b. And let's say that a is equal to 1. In Python, you can just start by naming a variable. Here is a, and just declaring it as equal to 1. Python will understand that as an integer. And let's hit enter, and let's say b equals 2. So we have a second integer b, and we're going to say that's 2. And then our third integer we're going to call c, and maybe you guessed it, c is equal to a plus b, and that is just as simple as exactly typing that. C is equal to a plus b. And if you'd like to see the output of that calculation, we'll review this more later. So not super important to understand it now, but just for now, believe me when I say that you can type print parentheses c. So a equals 1, b equals 2, c equals a plus b. And then print c. And then we'll execute it. And what do you know? We get a 3. So you'll notice here that in Python, this is as simple as just naming something and just telling Python what it is. In this case, we wanted to assign simple integers to names of variables that we can then later refer to by name when doing subsequent calculations. And we can name the results of those calculations and assign them to variables according to how we name them. In this case, saying that the result of our named variables a and b, we'll name that and assign it to a variable called c, and then tell Python to do something with the variable that we assigned the result to, that here being c. And in this case, just doing something as simple as printing it to screen. And that brings us to the very basics of what are called types. So in various programming languages in Python, you have lots of different ways that we can represent data. And in the very simplest case, we can take data and assign it a particular type for a representation of a particular piece of data. In this case, we just said that we had two integers equal to 1 and 2, and we were going to represent that data in our executable software using the variables named a and b. And when we do this, somewhere in memory on our computers, the integers 1 and 2 are stored in memory, and we can refer to them by the names that we've assigned to them using these assignments. Now, scalar types are types that work with single pieces of data, but those can be different types of data. When you consider, say, the difference between 1, the integer 1, and something like 1.1. Or say, consider the difference between the integer 1 and say the character egg. In Python, these are treated differently, and these are all called scalar types. So these types of data that are scalar, most importantly, cannot be subdivided. So when you have a single piece of data like an integer or say a string of characters, those can't be divided up into say sub-elements of data, and hence they're referred to as scalars. So to get us started, scalar types that are available in Python for numbers and booleans, we have integers, which are just called int, int. So here, A, B, and C, all of these have a type called int. Whereas, say, a variable that's been assigned a real number like 1.1, 5.1, 7.6, anything with decimal precision is called a float. So there are ints for integers, there are floats for real numbers with decimal precision, and then there are Boolean value types that are just referred to, they're called bool. So you can have a variable, say D equals true, or E equals false. And D and E here are Boolean valued, and they are called, their type is called bool. So you can see what some of these look like, or you can check the data type of a variable. I'm actually going to switch out of Jupyter Notebooks and switch over to my favorite IDE, which is Pycharm. So here, say we have a variable D equals true. D here is a Boolean, and we can find that out by using a function type. We can say type parentheses and give it a variable. And when we print this, we'll find that Python will tell us that our type of our variable D is a bool. And you can find that you can do this the same for, say, D equals to 1. You get that it's a type int. D equals 1.1. Now it's a type float. Now it's possible to take data and actually convert it from one type to another. This varies in mileage based on the types of data that one is trying to convert from and to. So in some cases, it's possible to convert data from one particular type to another. In other cases, it's not possible at all because the conversion is not defined. Now that conversion is called casting or type casting. And in Python, for simple scalar types, it's possible to do something like the following. So say we have an integer a equals 1, and say we would like to have another variable b that is equal to a, but instead of it being an integer or an int type, we'd like to have it as a real number or a float. We can do this by doing something like this: b equals float a. And we'll find that when we print A and print B, my first entry of the print just shows a 1, and that's A. And then my second print shows 1.0. That's a float. Now it's possible to do the same for the other scalar type that we've already discussed, being the bools. So in this case, you'll have something like C equals bool of A. And this is a first example of particularities concerning the conversion of types from one data type to the next. If we say convert our integer A, which is equal to 1, if we cast that to a bool and assign it to C, what would we get for our value C? What is 1 interpreted as? 1 being an integer, what is that interpreted as in Python in terms of bools? And we'll find that in our third print, if we print C being equal to the bool of A, we get that it's equal to true. And we'll also find that if, say, we were to change A equal to 0, A would still be an int. And we'll find that if we cast A to a bool and assign it to C when A is equal to 0, now we'll find that the cast is equal to false. And so in the very simplest but of many different types of typecasting conversions. The convention is, in this case, that for integers, when casting an integer to a bool, we'll find that if the integer is equal to 0, that's understood as being false. Whereas if an integer is non-zero, is always interpreted as being true when cast to a Boolean. And there are lots of particularities concerning this. I see in the excuse me, in the chat, there's some discussion about rounding issues and what happens when, say, casting from an integer to a float or vice versa, along with particularities for that very common typecast. The list is endless of the details for casting data from one type to another. Python being among the simplest languages to do this in. And so what's most important here for our case now is that it's possible to convert data from one type to another, and that those conversions occur according to specific rules. For the case of our built-in types, our scalar value built-in types like the int, the float, the bool, those all have predetermined rules for converting from one type to another, most of which you can typically just figure out just by simple experiment, like what we've done here. For complicated types, the complexity can be endless. Now, we've already done a little bit of this, but in Python for writing expressions, in particular for mathematical expressions, expressions read from left to right according to order of operations as one would expect. So when doing basic mathematical calculations, like in our very simple case of when C was equal to A plus B, this simply just reads from left to right, A plus B. Whereas if one, say, doing more complicated calculations like A plus B, take that sum and multiply it by B, this follows the normal order of operations in that A plus B is first calculated and the sum is then multiplied by B. And Python provides all of the operators that one would expect for doing basic calculations for the case of addition, subtraction, multiplication, and division. These are accomplished as one would expect. So if A equals 1 and B equals 2, you can do all sorts of operations like A plus B for addition, A minus B for subtraction, for multiplication, A times B, the multiplication symbol being the asterisk, and A divided by B using the slash, and then two additional operators of interest, the first being calculation of the remainder. And the remainder operator is the percent symbol, and this is the remainder of A divided by B. Or if you're looking at the slides on my right, this would be the remainder of I when divided by J. And then lastly, for very simple operators, there's the power operator, and that is to take A to the power of B. In Python, the power operator is the double asterisk. So when taking A to the power of B, write A asterisk asterisk be. Now, Python is not particularly picky about spacing for the case of doing simple arithmetic like this. So A equals 1 with or without spaces in between, both are equally valid. Spacing becomes more particular and much more particular when we get more into control structures, which we will get to today. But for now, while I tend to find it a little stressful to read code that has no spaces in between operators, putting spaces in between or not, both are equally as valid for doing arithmetic operators.
Hey, TJ,
Jim,
put a space in front of your first line and run it.
yeah, error.
Yeah. So Jupyter doesn't handle spaces correctly. Because if you do that in Jupyter, it doesn't throw an error.
It does not.
And I tried idle as well. Idle also throws an error. And I could have sworn that that's serious Python S, is that those spaces absolutely positively always matter. So it's interesting Jupyter doesn't catch it. Anyway, okay.
Yeah, so in the case of having preceding spaces that may or may not produce errors depending on what's actually parsing the code, has everything to do with in Python, the way that control structures are constructed is using indentation. And we'll visit this a lot more later, but putting sort of like erroneous spaces before the beginning of a certain line of code can confuse Python very quickly, because Python actually uses preceding spaces to understand your intentions concerning the actual flow of your software. In a very simple example, writing a block of, say, conditional statements of if this, then do that, so on and so forth, can look in Python like this. Python will understand this, with preceding or with successive layers of control logic based on the actual indentation. So if you find yourself putting lines or spaces before your lines of code and getting seemingly strange errors, this has everything to do with that Python very much cares about the spaces you put before the beginning of your line of code. Now, once you actually start writing the code, that so much doesn't matter, at least not for operators like this. All right, let's continue. Yeah, as mentioned, ordinary order of operations apply for doing arithmetic calculations. Now, we've been doing this for a little bit now today, and that is assigning variables. So again, you want to take a piece of, say, data and actually assign that into the memory of your computer for subsequent calculations or processes. We do this just by, in Python, just declaring a name of a variable and then assigning it some sort of value. This can be done successively for the same name. A equals 1, A equals 3, A equals 5. You'll see my IDE is showing me warnings saying, basically, what are you doing? But this is all valid. This can get more particular for more complicated data types, but for the case of floats and spools, this is all perfectly fine. Now, one thing to note is that when doing a set of calculation, like a procedure of calculations, is that variables that have been derived, their values that have been derived from actual calculations, don't necessarily automatically get updated if they've been calculated from other variables. And what I mean by this is that in our very simple example of adding two integers, we had a equals 1 and b equals 2, and then calculated c equals a plus b. Now in this case, here I'm referring to my screen at line 3, c will be assigned the integer value of 3. Now, if after calculating c as the sum of a and b, if I then assign a new value equal to 2, c does not change automatically, in that this calculation, this value that's been derived from a set of arithmetic operations on previously declared variables, is not automatically updated when constituent data that makes up the operation changes. There are particularities about this for more complicated data types, but in the case of operations on scalar data types like floats and spools, if a value has been assigned to a variable that's a result of some operations on previous variables, the value of that variable does not update when the constituent data that made up its operation result changes. So in this case, at line 4, when I reassign a equals 2 and I print c, I will find that c is still equal to 1 plus 2. Of course, I can redo the calculation to update the value of c, but the update does not occur automatically. Now, the other interesting sort of primitive built-in data type is the string. And the string is a sequence of characters. Those characters can be numbers, they can be letters, but they are declared using a set of either single or double quotation marks. Say I want to declare a string, and the string is a message to all of you that says hello. I can do so in a pair of single quotation marks and then just type hello. Now, our strings can contain both letters and numbers. They're just all understood as characters in a string. And so I can say for some string B, with spaces and everything, the date is 8/1. And that is all a string. And I could, again, put that in sets of single or double quotes. I can have spaces, I can have numbers, and both of these are the same data type. They have different values, but they have the same data type, and the type is a string. Now, strings have their own operators defined on them. And in the case of joining strings, say I would like to take my first two strings that says hello and then states the date. I can join those into a third string by just adding them. Let's say C equals A plus B. And this is to say that the string C is equal to A with B added to the end of it. Fine, when I print C, I get my A string, hello, my B string, the date, and then my C string is both A and B without any spaces in between. And this operation can be done in to an arbitrary number of occurrences of addition. So in this case, if I say wanted to put a space in between A and B when making my message, I can actually just do so right in line by doing A plus, and then a string with just a space in it, and then adding B. A, which is hello, plus a space, plus B, which is the date. And now when I print that, I get a message that doesn't look so silly. And the strings also have all sorts of other operators defined on them. For example, if I multiply a string by an integer, that's what I've done here, A plus a space plus B times 3, and then I print that, I actually find that I get 3 repetitions of the string that I multiplied by 3. This is true for a couple of other data types, but here's sort of your first look at having operators assigned for different data types, particular to the data type, that may or may not be what you expect. Multiplying by 3 for a string results in a repetition of that string by the number of integers that you multiplied by. Now we've done a lot of print already. So the print function will take a string and print it to a terminal, whether it's in Jupyter Notebooks or in my case, just in my IDE. Got an integrated terminal here. And that's how I've been printing data in my case. And print understands a lot of data types, but not all data types. In the case of integers, floats, bools, and strings, print automatically understands that when given, say, an int or a float, it understands to first convert it to a string and then print the string to the terminal. That's actually what occurs when I say print 0. And I run that and I get a 0. 0 is not actually being printed per se, not the int, but actually a string of the int. And print knows how to do this for lots of types, but not all. Later today, towards the end of the day, we'll go through how to actually define that operation on data types that we design ourselves. But what's true is that, say, print when passed 0 is the same as casting 0 to a string. And string, the casting function is str. So int was for integers, bool was for booleans, float for real numbers, and then lastly, str for string. And you can do this for assignment as well. So you can do C equals str of 0. That will do the same here. Do just a bunch of zeros, still get a 0 for the string. Whereas if I were to say do D equals these, but inside of the quotation marks, there's a difference. A bunch of zeros in the case of Python, just a bunch of zeros all in a row is the same as an int of 0, whereas putting a bunch of zeros in a set of quotation marks is a string of all of the zeros that are entered in the set of quotation marks. You can see that difference shown here. All right, let's do a quick poll, make sure everyone is with us so far. Just give everyone a second to respond to that. Make sure we haven't lost anyone so far. Main takeaways here being that we have our ints, our floats, our bools, and our strings. We can convert data from one of those types to another with rules that are particular to the conversion or the cast. And each of those types has operators defined for them, like using the addition symbol, the multiplier symbol, and they can have different meanings depending on the type that's being operated on. Those are the takeaways.
Excuse me, could you please tell a little bit about the shortcuts that you use for selecting the text in a fast way, you know, like you're jumping between the, like selecting them, I think using the shortcuts, specific parts inside the quotation. I mean, the keyboard shortcuts, I mean.
Keyboard shortcuts for, like, say, executing code in Jupyter Notebook?
No, in the Pycharm, for example, you select, like, I think you press shift and use the arrows to select them. Then these kinds of shortcuts.
Oh, or some of it's AI.
Like that, so.
Yeah, so some of this has to do with the AI being trained to my coding behavior. But yeah, for say executing a script in Pycharm is Control-Shift-F10 on Windows. These other things, you know, all the suggested code, yeah, like that. That's a combination of just built-in configurations for Pycharm for the language, and then studying me. But those mostly come up automatically. All right, so let's, I think we're good. So let's continue on. If you're a little bit lost or this is kind of whirling around in your head, don't worry so much about it. We'll get a lot of practice on this today. But let's continue. So another type of operation that we can do is we can say compare data, the result of which being a bool. We can say, is something, say, greater than something else? Are two pieces of data equal? Are they not equal? So on and so forth. And this looks like something you can see here on the right. We're doing some very simple tests that I'm just going to make up on the left. So if we have our a equals 1, our simple integers, a equals 1 and b equals 2, we can ask, is a equal to b? And assign the result of that question to a variable. In this case, we'll call it c. We'll say c is equal to the result of testing, is a equal to b? And that operation is a double equal sign. A equals b is the test, is a equal to b? And we can assign the result of that test to a variable, again, calling it c. And when I print c, I find that c is equal to false. A is not equal to b. And when I change A equal to say 2, then I find that the test is true. Now reverting and saying A is equal to 1 and B is equal to 2, we have lots of other operators like greater than or equal to. These are all using the comparison operators that one would expect. Maybe the most peculiar one is, in this case, the test for inequality. So if we have the test for equality being the double equal sign, then the test for inequality being the negative or the negation of is exclamation mark equals. So A exclamation mark equals B is the test. Is A not equal to B? And now I'll find that when A is equal to 1 and B is equal to 2, I will get in the test for inequality my result C equal to true. So you can do this for different types of data in comparisons with varying mileage. So for some data types, the comparison to other data types is not defined. Much of this you can see here, I've tested on the test for equality for an integer and a float. And I get that the result is false. When I test A equals int of 2 and B is equal to the float 2.0 and I test for equality, I find that that actually returns that it's true. So Python understands a comparison of ints and floats under certain conditions. And again, different data types have comparison operators defined on them with respect to other types of data, most to do with how data is converted during a typecast. So mileage varies, very particular to the types of data that you're working with. This is one of those times where when in doubt, check Google. Now, there was one data type that we've kind of neglected a little bit, and that's a special data type, which in Python is called the Nun type. And the Nun type, for anyone who has worked in, say, like C++, Nun is the Python equivalent to null, which is a special value that roughly equals, or is roughly interpreted as nothing. And the abstraction and philosophy of this, I would like to not get into so much today, but suffice it to say that the Nun type has exactly one possible value, and it can be assigned to any variable. And the value is a reserved word, none, with a capital N. C is equal to none. And this special value can be compared to any other data type that's in memory. And one can always ask something like, if I say that C is equal to none, I can ask, is A equal to C? Is A, the int 2, equal to none? And the result is false. Now I can say also A equals none and C equals none, and then test for equality, and I find that that's true. These are unique variables, both of which have been assigned the same value, and the value is the Nun type. And there's a special test for the Nun type, one that we've not covered yet. And the test looks like this. If I want to ask, is a variable equal to the Nun type? So without regard for what the type the data might be, I can simply ask, is a variable the Nun value? Or is it equal to the Nun value? And I can do that by saying, say, in this example, D equals the test C is none. So the operation test for a variable being equal to none, irrespective of its type, C is none. And the test for inequality intuitively is the expression is not none. The test to see if C is not equal to the none value is the expression C is not none. And I find that in this case, I assigned C equal to none and then tested C is not none, I get a resulting value of false.
Does equal work? I think it does.
Yes.
Or exclamation equal.
Yeah, so these operations are defined, the equals and the exclamation equals. But you'll note that my IDE at least will show a warning and that this is not a recommended expression. So you can do either. Most typically none is used for working with more complex types of data, in which case one can ask, has a particular type or has a particular value of some complex type been assigned to my variable? The options being that it either has or my variable is assigned the none value, in which case the test is according to C is none. This question is more about the IDE and not about the language stuff. It's to do with the language. There are some expressions that are supported that are not recommended. And so you may find that you aren't getting some of the little warnings in in your notebook that I'm getting in my IDE. And that's because Pycharm will tell me about when I'm doing something that's not recommended. Just like Pycharm will also tell me when I'm doing something that's illegal. When I do something that violates a syntax rule, I'll get a warning for an error. This can also be configured to tell you when you're doing something that technically Python will execute, but most people will frown upon if they see it. And that can be for various reasons, most of which are unimportant to us. In general, I try to stick to the recommended syntax. But yes, as Juliana points out, Python is very liberal in what it will execute because it's what's called an interpreted language. But because Python is so flexible with what it will execute, there tends to be a lot of recommendations about how you write your code. When it can do nearly everything, it's important to try to focus all of the creativity towards something that's comprehensible to others and to yourself, your future self. All right, let's continue on. Now we're gonna do, if I remember correctly, this is the last bit for our first module today before a quick exercise, and then we can take a break and stretch our legs. And sorry, I'm gonna get more and more hoarse as the day goes on. Forgive me. I'm gonna try to keep drinking water and hopefully I don't sound like a frog by the end of the day. So the last thing I think that we're going to do for this first module is we're going to do what we talked about a little bit with an excellent question that was asked earlier about why does Python sometimes fail when I put spaces before one of my expressions. And we talked about that Python cares about the spacing before your lines because it uses that to determine some of the flow and the logic of your software. And what I mean by that is that in Python and in other programming languages, one of the most useful things that you can do with software that you develop is to do what's called branching. And that is to design your software to make decisions and execute things based on those decisions. We've done, for example, the comparison operators. We had our simple, silly integer example of saying A equals 1 and B equals 2, and then test is A equal to B. Now, what's important is that based on those types of tests, like a test for equality or inequality, we can tell Python to execute certain blocks of code based on conditions that we express. Based on our conditional tests, we can execute certain lines of code, and that's called branching. And in this first example that you can see here on the right, we can do what are called if statements or if blocks, depending on who you ask. And they look like what's shown here. The basic structure looking something like this. This is true for all if statements. You can initiate or designate a block of code that is only to be executed under certain conditions using the template like what's shown here, where condition is the outcome of some test. In a very simple example, we go back to our A equals 1 and B equals 2. Here we'll say for C, C is the result of the test of whether or not A is equal to B. So C equals the result of the test for equality of A and B. Now C here is a bool, and bools can be used to designate or specify the conditions of a branch in our control flow. And I can do that like this. If I say if C, my bool C, if C colon. And then if you're following along, I'm going to return, and you'll notice that my IDE automatically adds a tab. And it does this because everything that follows in this block that is tabbed will all be considered as part of this branch that will only be executed if C is true. In this case, I'm just going to do something very simple. I'm going to say that if my test result C is equal to true, I'm just going to print the string that says true. Now, when I run this, A equals to 1, B equals 2, C is the result of the test for inequality. And now I'm only going to print true if my test for equality is equal to true. And when I execute this with A equals 1 and B equals 2, I get nothing printed. Now, if I change B equal to 1, which is what A is also equal to, and then I test for equality, now C will come back as being true. And when C is true and C is used as my condition, and I execute this, I find that now my software, my program will print true, and that is because the condition for this block of code is true. Now this is applicable for all of the comparison operators that we reviewed, as well as the tests for the none value. So if C is not none, so on and so forth. You can do these conditional evaluations inline in this if block. So instead of saying that if C, then do my code block, instead I can just write into this conditional statement, if A is equal to B, print true. And I find when they're not equal that my software prints nothing. When I make them equal, it prints true. Now, to continue on with that, it's also then possible to construct additional branches for our logic. The two other options, the first being to test for another condition on the condition that the preceding condition failed. Meaning, if the test A equals B fails, if I would like to test another condition, I can do that by starting another conditional statement, which is elif, E-L-I-F, which is a combination of else if, something like that. Elif, E-L-I-F, and a colon, and then return and indent, one tab. And elif also needs some sort of condition. And say, in this case, elif A, say, is less than B. So if A is equal to B, then do something. And if that's not true, then test is A less than B. And then return with a tab. And then I'm just going to print the operator, my less than symbol. Now let's try that. A is equal to 1 and B is equal to 2. My first branch did not evaluate because my condition A is equal to B was false. And then since that condition was false, then my next condition described in elif is then tested as A less than B. And in this case it was. And so this block executed. Now, the very last aspect of this is to specify a sort of last resort. That if all of my tests, because there are, you can define these infinitely, A less than 2 times B, so on and so forth. You can do as many elifs as you'd like. But then lastly, it's also possible to describe the sort of last branch that occurs if nothing else occurs. If all of my if statements evaluate to false, but I would like to have something that executes instead, I can specify that using else. And else takes no conditions. It's just else and a colon, return and then tab. And that's it. So now I find testing for A is equal to B or A is less than B. Else just print else or whatever nonsense you'd like. And in this case, let's say A and B are both equal to 2. When we run this, we get true. That was from here. A is equal to 1, B is equal to 2. I get my less than operator. That was printed from here because this was true. Now when I say A is equal to 3 and B is equal to 2, I get a printed else exclamation. That was here. And that was because A was not equal to B. And also A was not less than B. And that's control flow, at least using if statements.
TJ?
Yeah.
Show an example of more than one indented statement.
Mhm.
And then a statement that's not indented that actually shows that you've ended that control structure.
Sure. So it's possible to nest these structures. So within, say, a branch here, I can then also start another one and say,
Well, do the simpler one. So print true, print 47, A equals 96. They're all in the same indentation level. They're all executed with that thing. You don't necessarily need another layer of indentation, right? The whole thing about the space indentation is you can have as many lines indented as you want, and they're all part of that same code block, and you do as much as you desire to do there. And the whole thing ends the first time you get an unindented line that's not a clause on the if.
yeah. So then to get out of the block and start back in the main branch of a code, just go back to no indentation and say something like that. So each of these is executed conditionally based on conditions. And then once we're done with this set of control logic, then we can just remove the indentation or go back to the original level of indentation at which we were operating before this branching. And then continue on as we were. And that's true for nested blocks as well. So you can do things like testing for A being greater than 2, but only under the condition that A is equal to B, versus if A is greater than 2, but only under the condition that A is less than B. And then once I've done my nested logic, then going back to the level of indentation of this block, and then continuing on. So maybe you get a stronger sense now of why putting spaces before lines of code can potentially throw some errors depending on how your code is being parsed. All right, and then probably reserve this exercise for our break since we've kind of gone through most of this and I really don't want to get behind today. So I'm going to leave this up. We're coming up on a 15-minute break. We've got a module questionnaire running. If everyone could fill that out with brutal honesty, it would be very helpful for improving this content and these exercises and so on and so forth. So please, we appreciate the feedback.